The counterintuitive nature of quantum mechanics seems to spare nobody. Even Albert Einstein was particularly concerned about the absurdity of the reality predicted by quantum mechanics. But on the other hand, Niels Bohr had his firm belief on the theory and the results predicted by it. This led to one of the most famous debates in the history of science and also resulted in some important theories. Niels Bohr thought that it is meaningless to assign reality to the universe in the absence of observation. Without observation, the system remains in the mixture of all possible states, which is known as superposition. Whenever an observation is made, the system is found in any of the possible states. But this also means that without observation, we do not have any idea of the system. Einstein was uncomfortable with this idea of reality. He insisted that the wave function and by extension quantum mechanics is incomplete. There must exist what we call hidden variables that reflect a more physical underlying reality. In order to prove Bohr's idea wrong, Einstein along with Boris Podolsky and Nathan Rosen proposed a paper where they showed that to abandon the idea of realism, we also need to abandon the idea of locality. In physics, the principle of locality states that an object is directly influenced only by its immediate surroundings. Locality evolved out of the field theories of classical physics, which says that for an action at one point to have an influence at another, something in the space between those points, such as a field, must mediate the action. This is fundamental to Einstein's theory of relativity, which tells us that information between 2 points cannot propagate faster than the speed of light. The Einstein-Podolsky-Rosen or the EPR paradox introduces one of the most mysterious and exciting ideas in quantum mechanics, quantum entanglement. Here's the idea. Two particles interact briefly, they influence each other so that their properties are somehow connected, and yet we refrain from measuring these properties to preserve quantum uncertainty. Quantum mechanics requires that we describe the particle pair with a single combined wave function that encompasses all possible states of both particles. We call such particles an entangled pair. Now, according to Copenhagen interpretation, any measurement of one of the particles automatically collapses the whole entangled wave function. So, theoretically, measurement of one particle gives information about the other. That's an influence which can instantly cross any distance or even back in time, violating locality and probably causality. Einstein was very much uncomfortable with this idea. He thought every single point in the universe is well defined by knowable quantities and hidden local variables which could affect each other not faster than the speed of light. Although the argument between Bohr and Einstein was philosophical at that time, Irish physicist John Stuart Bell in 1964 proposed an experiment to resolve the debate. The experiment included electron-positron pair. When spontaneously created from a photon, electron and positron will always spin opposite to each other. But until measured, we are unable to tell in which directions are they spinning. We just know that they spin in opposite directions and their wave function is entangled. In such case, measurement of one such particles give information about the other no matter how far they are apart. But in quantum mechanics, measurement does have an effect on the system. In quantum spin, the effect is especially weird. We define spin direction according to spin axis and the axis can point in any direction in space. But to measure spin direction, we need to choose an axis to align our measuring device. What we always find is that the observed quantum spin aligns itself. If we measure vertically, the spin will be up or down, and for horizontal measurement, the spin will be right or left. So measurement affects the spin of a quantum particle. But how does it affect its partner? It turns out that there can be two cases. Case 1, Einstein was right. In that case, the response of all possible spin measurements is encoded in each particle at the moment of their creation as hidden variables. So we can do nothing to one particle which can affect the other. When we measure their spin, we find a correlation in our results because the particles were once connected, but there will be no effect due to our choice of measurement axis. For example, let us take two boxes and a pair of hand gloves. We put each of the gloves in separate boxes without looking, and then the boxes are taken far apart from each other. Now, if we open one box and see the right hand's glove, we can say that the other box has left hand's glove even if it is far apart. In case 2, we assume Bohr was right. After creation, positron and electron may exist as wave function of all possible states. In that case, measurement of one particle spin will collapse the entire function and force the system to take on different values. The particle will then have opposite spins. That should lead to a correlation between our choice of spin axis for the first particle and the spin direction of the second particle. Now, this indeed is spooky action at a distance for which Einstein was uncomfortable. In order to resolve this, John Stuart Bell figured out a set of results known as Bell inequalities. It said that we would expect that Einstein is right and quantum systems need local variables. If an entanglement experiment violates the Bell inequalities, then local realism is also violated. But performing entanglement experiments are not so easy because it's very difficult to produce entangled pairs and even harder to maintain the entanglement. In 1982, French physicist Alain Aspect succeeded to produce a result which violated the Bell's inequality. He used polarization of photon instead of electron and positron pair. In the experiment, a source emits a pair of entangled photons V1 and V2. Their polarizations are analyzed by two polarizers which are aligned along directions A and B. A and B can be along x, y or any direction in the xy plane. Each polarizer has two output channels labeled +1 and -1. A photon polarized parallel to the direction A or B will be detected as +1 and -1 if they are polarized perpendicular to the direction. But in general, photons are not in a state of polarization corresponding to a specific output channel. For the entangled state of two polarized photons, quantum mechanics predicts that the polarization measurements performed at the two distant stations will be strongly correlated. Aspect found that there was a correlation between the choice of polarization measurement axis of one photon and the final polarization direction of its entangled partner. Since then, many experiments have verified this result over and over again for larger distances. The instantaneous influence has been seen for over few kilometers at this point. Another experiment known as delayed choice quantum erasure also violates Bell's theorem. It has now been thoroughly confirmed that the Bell inequalities are violated, suggesting that the wave functions do not contain any local variables. So does this confirms the Copenhagen interpretation and disproves locality and realism on which the theory of relativity relies? Well, it turns out that entanglement might violate locality but not realism. In fact, it was Bell's opinion that the violation of his inequality would only violate locality and not realism. But non-locality implies that information travels faster than light. This might seem a direct contradiction of Einstein's theory of relativity. However, non-locality and relativity might be perfectly consistent. Relativity requires that causality is preserved so that there's no faster than light travel. But none of these entanglement experiments allow any real information to be traveled between the particles. It's only possible to see influence after the measurements have been made and are compared. As for the Copenhagen interpretation of EPR paradox, we assume that wave functions are not real, and wave function collapse is interpreted subjectively. The moment one observer measures the spin of one particle, he knows the spin of the other. However, another observer cannot benefit until the results of that measurement have been relayed to him at less than or equal to the speed of light. And so, the Copenhagen interpretation remains consistent with all quantum observation. So it seems Niels Bohr's idea of universe is correct. However, the idea of realism and hidden local variables also stand out as long as they abandon the idea of locality. For example, the two entangled particles may be connected dimensionally by Einstein-Rosen bridges or wormholes. They allow instantaneous contact even between great distances. Also, the De-broglie pilot theory works by assuming real and non-local variables. In addition to a wave function on the space of all possible configurations, it also postulates an actual configuration that exists even when unobserved. The evolution over time of the configuration is defined by the wave function by a guiding equation. Apart from all of these, there might be another way of explaining quantum entanglement without abandoning the realism and locality concept. This is known as many world interpretation. So even though Einstein was much uncomfortable with the idea of reality predicted by quantum mechanics, it is undeniable that the debate between him and Niels Bohr paved the way of theories like quantum entanglement and Bell's theorem. Quantum entanglement plays a big role in quantum computing, which uses qubits. I previously covered how quantum computers work. You can check it here. Thank you for watching this long video. Hope you enjoyed it. If you did, please like and share this video, and to see such videos in future, do subscribe.